Hi, Year 9s. Welcome to the final class for Term 1. It's difficult at the best of times to run a maths class during Period 5, let alone the last class in the last week. I know that you don't want to do a lot of work right now, and I understand that. So what I'm proposing to do is to just show you a little bit of maths. Won't go for too long. Then I'll let you do a quick search on the internet. And then once you've done a little bit of work for me, I'm happy for you to play some math games or watch some videos or watch a movie. It's up to you and up to your teacher. So in this video, what I would like to do is introduce you to something called irrational numbers. I know that name sounds strange. It's actually a really nice follow-on from the work that we've just done on indices. And you might never come back to the study of irrational numbers, depending on which maths class you go to next year. However, I think it's really important that you have at least seen what an irrational number is, that you understand its significance, and that you get a sense of what numbers actually are and what they do. So without further ado, let's get underway. I want to begin by posing the question of what kinds of numbers we work with in everyday life. We start off, when we're very young, with whole numbers. Numbers such as 1, 2, 3, 4, and etc. There's another useful number, which we call 0, to represent nothing. And these numbers, they sort of answer questions that go along the lines of how many. So, for example, how many chairs are in the room? How many computers do you have at home? How many oranges can you fit into a box? All of these questions are very naturally answered with whole numbers. And there's a special name that we give to these numbers. You may never have used this name before, but in the world of mathematics, that name is the natural numbers. And just very roughly, you can think of these as 0 and the positive whole numbers. Now, think about the maths that you've done over the last 9 years. Are these the only numbers that you've worked with? Now, the answer would be no. You're probably thinking of fractions and decimals, but there are other numbers that you've used as well. A very simple way to extend this set is to ask the question, can I go the other way? Can I keep counting back below 0? Well, if you want to capture that, we need to invent a new kind of number. And this happens around grade 5, grade 6, grade 7, where you introduce the negative numbers. And so that brings us to our second number system. This is called the integers. And these are whole numbers, which are positive, negative, or 0. So I could have -3, -2, -1, 0, 1, 2, 3. And I can keep going up, but I can also keep going down as well. And I'm going to represent this with the 3 dots on either side. Notice that the natural numbers had a starting point at 0, whereas integers, they don't, because they kind of go both ways. And at this point, we have something resembling a number line with discrete intervals at each whole number, 0, 1, 2, and 3. Now, I'm going to ask the same question. Are there any other numbers that you've worked with? And the answer is yes. We can nuance our answers to questions such as how many. So for example, suppose I gave you a really large pizza to eat. How much of a pizza can you finish? If you can finish the whole pizza, then you would answer with 1. If you didn't eat the pizza at all, you would answer with 0. But if you couldn't eat the whole pizza, you would need a number that was less than 1, but larger than 0. I would need a way to represent a part of a whole. And the easiest way to represent parts of a whole is with fractions. And so the next number system, which is called the rational numbers, captures all possible fractions. And specifically, fractions involving integers. So here, I'm just going to write this as the set of all possible fractions, a divided by b, where a and b are integers, and I need to make the restriction that b is not 0. And that's because we're not allowed to divide by 0. Division by 0 is undefined. I won't go through that in this video. You're welcome to look it up online. It'll take about 5 minutes to understand that. Now, can you see? The natural numbers was the simplest number system. And I want to say, before we get too far along this, that with the natural numbers, I can do addition, and I can do multiplication. However, I can't really do subtraction. Because if I take two natural numbers such as 1 and 3, if I try to take 3 minus 1, I get 2, another natural number. But if I try to do 1 minus 3, I can't get another natural number. In order to introduce subtraction, I need to move to the integers. And now I can take any two integers, perform subtraction, and get another number which is also an integer. Similarly, when I move from the integers to the rational numbers, now I can perform a new operation, which is division. I couldn't do division with the natural numbers for every possible pair, or with the integers. But once I have fractions, then I can do division with any two numbers that I choose. And get another rational number. So we started with a very basic number system. We introduced a new operation, and that allowed us to do more sophisticated things. Now, the question that I want to put on the table for this lesson is, are there any other kinds of numbers? Can we, as human beings and students of mathematics, make sense of the real world and do everything that we want to do with just these three number systems? That's the question. Are these three number systems enough? And a surprising answer to that question is no. And a related question that was raised more than 2,000 years ago was, consider this system, the rational numbers. Is every number rational? The shocking answer to that question is no. And I've got two very simple examples. The first example involves constructing a right-angled triangle where the length of the two shorter sides is 1. And I'm interested in how long the longer side is. Turns out, if you try to write down a number to describe how long that side is, you can't do it with a fraction involving two integers. You can't do it with the rational numbers. We get this strange number, which we call root 2, and I know that you have this button on your calculator. The amazing thing is, I can't express root 2 as a fraction of two integers. Can't be done. So it's not a rational number. Now, it's very easy to draw a triangle with side lengths 1 centimeter and 1 centimeter. Surely I can measure this side. But there you go. Something that I can measure with a ruler. And I can't capture it with a rational number. It's shocking. And legend has it that among the ancient Greeks, when this was first discovered and someone put this argument forward, the community of the day was so scandalized by this, legend has it that that person was drowned. It was too difficult and too hard to accept at the time. Maybe maths isn't so boring after all. Now, let's look at this second example. This is one that you have seen before. You've seen a circle. You can pick up a compass. You can draw a circle. The question is, how far is it to go round the circle once? How long is the perimeter or the circumference of the circle? And if you remember your work from year 7 and 8, you'll remember that the answer to this question is 2 pi. And this number pi, it was a bit mysterious. You know it's 3.1415, but that list of numbers never ends. And there's no pattern to those digits. It just goes on forever. This also can't be expressed as a fraction of two integers. So we were pretty happy until this point. We had 3 very simple number systems: the natural numbers for counting, wholes. We had integers, which captured negatives, and we had rational numbers, which captured parts. And yet, in everyday life, with things that we can measure and things that we can draw, we can't adequately capture them with the number systems that we have so far. So, what are we going to do? Well, we're going to need to introduce a new number system. And the work of actually doing this is really quite substantial. This took hundreds of years. We're not going to rehearse all that work now, but the main thing I wanted you to take away from this lesson is not all numbers are rational. So what are we going to call these numbers? If they're not rational, we are going to call those numbers irrational, as the title of this lesson suggests. So the real numbers, which is our new number system, will consist of the rational numbers plus the irrational numbers, which informally I will call the gaps between the rational numbers. Now, one other fun thing I want to say here is the natural numbers supported addition and multiplication. The integers introduced subtraction. The rational numbers introduced division. What operation is introduced by moving from the rational numbers to the real numbers? This is a really deep question. It's only answered properly in university courses. But I will tell you what it is. It's called a limit. So once we introduce the real numbers, we are able to take limits of sequences of rational numbers. If any of you are planning to take more maths after year 10, take a look at limits and see the kind of cool stuff you can do when you move from the rational numbers to the real numbers. Okay, so key takeaways for everybody. I hope you can tell that I enjoy this topic and that I like maths, but this is a year 9 maths class, and I want to focus it on things that are important for you as well. So here's what I want you to know. Number 1, I want you to know that not all numbers are rational. That's the first thing I want you to know. The second thing I want you to know is that the numbers that are not rational are called irrational numbers. That's pretty easy to remember. And based on those two things, I'm just going to do one final slide with some examples where I give you a bunch of numbers, and I want you to tell me whether the number is rational or irrational. And the way that I want you to think about this is every natural number is an integer. So everything inside the natural number circle is contained inside the integer circle. So all natural numbers are integers, and all integers are rational numbers. So that means natural numbers and integers count as rational numbers. But there are some rational numbers which are, I should say it this way. There are some real numbers that are not rational numbers because they're not contained inside that second circle. And what is missing from the rational numbers are the irrational numbers. So think of the real numbers are, I should say the real numbers, think of them as the rational numbers plus the irrational numbers. So if I combine those two sets, I get the real numbers. Okay, let's finish. Here are some examples. So at the year 9 level, this is all we need to be able to do. I'll give you a bunch of numbers, and I ask you the question, is it rational or irrational? And because we've finished our work on indices, we might not have the chance to ever go back to this topic again. And I think that will be a real shame to get through year 9 maths and never look at what an irrational number is. So let's quickly work through this. Let's start with the number 2. The number 2 is a natural number. And remember, all natural numbers are integers, and all integers are rational numbers, and all rational numbers are real numbers. But the real numbers introduce the irrational numbers. So anything that's not rational is irrational. Now, the number 2 counts as a natural number. And the natural numbers are included in the rational numbers. So, number 2 is rational. Even though it's a natural number, the natural numbers count. Okay, 2/5. Here, we need to remember what a rational number is. It's a fraction involving 2 integers. The numbers 2 and 5, those are positive whole numbers. Integers are whole numbers which are either positive, negative, or 0. So we have a ratio or a fraction involving 2 integers. So yes, this is a rational number. Now, if the number is negative, does it still count as rational? The answer is yes, because a rational number involves a fraction of 2 integers. Integers can be negative. So -6 is rational. -3/5 is also rational. Think of -3 as the first integer, and 5 as the second integer, and those 2 integers in a fraction. Okay, I'm going to start with root 9. Is there a number which, if I multiply it by itself, gives me the number 9? The answer to this question is yes. And that number is 3. If I square the number 3, I get to 9. So even though there's a square root symbol, this is actually simplified to the number 3, and 3 is a natural number, which means it is rational. So just note, just because you've got a square root, it doesn't mean it's always going to be rational. Sometimes you have special numbers like 1, 4, 9, 16, 25, 36, 49, 64, which are all perfect squares. And if you take the square root of a perfect square, you're going to get a whole number, which is rational. However, root 8 is very different. This number is not a perfect square, because 2 times 2 is 4, 3 times 3 is 9, and 8 is between 4 and 9. So this is not a perfect square. I can't get a whole number when I square root this. So this is irrational. Okay, the number pi is irrational. If I take an irrational number and divide it by 3, it's still going to be irrational. Now, you might say to me, Mr. Chu, this looks like a fraction to me, and I thought fractions were rational numbers. And you'd be correct, but it's not just any fraction. It's a fraction involving 2 integers, and pi does not count as an integer. So, even though it's a fraction, it's not a rational number. So please remember, not all fractions are irrational numbers. And finally, 3 divided by pi. It's not obvious, but if you divide by an irrational number, chances are you will end up with an irrational number again. And so we can safely assume that this is irrational as well. Okay, that concludes our work in term 1. And I will leave a very short bit of internet research for you to do in this class. It will take you about 5 minutes, and I'll describe it now. So all I would like you to do is do some research on the internet. So use the internet to research one of these 3 irrational numbers. Okay, so you have 3 choices. The first irrational number you can look at is pi. spelt Pi. The second irrational number you can do some research on is E. This is called Euler's number. And the third irrational number that you can look at, it's a Greek letter, just like pi. It's written a bit like this. You should look up what's called phi, or the golden ratio. So here's my advice. If you don't like maths that much, and I understand that, we can't like everything. If you don't like maths that much, the easiest one to do research on is this one, the golden ratio. Just search golden ratio in art and nature, and you'll see all kinds of examples of the golden ratio appearing. It's really quite fascinating. If you're heading into higher level maths, so perhaps you might take maths methods or a university course that requires some maths, I recommend you look at either pi or E or both. So what I'm going to ask you to do is go on the internet, search up one of these three irrational numbers, so just one, and see if you can find 3 interesting facts about it. So I want 3 interesting facts, or applications. So by application I mean where it is used or where it appears. So for example, where can I find the golden ratio in art? Or where can I find the golden ratio in nature? Give me 3 examples. If you're heading towards banking or finance, maybe have a quick look at the number E. This is probably the most difficult one. So if you find this one a bit hard, maybe try pi or phi, but I'm just putting it out there. Okay, that concludes our video. So thank you, Year 9s, for indulging me with these 2 videos today. I know it's not easy to listen to a video because you have to pay closer attention. You actually have to work harder to listen to a video because you don't have the person in the room taking questions and sort of adjusting to you. So I also want to thank you for your patience as I found my way at Lyndhurst, and I want to wish you all the very best with your future study and your future careers, and hope it all works out well for you. So good luck, and wish you all the best. Thanks.